All right, we're done with Unit 4 and we're ready to take a look at the practice test. So let's go ahead and get going on this as normal. We want to make sure we show all our work and thinking. We want to write our answers in the correct format, and we want to make sure we circle our answers so everybody can tell we know what the answer is. So on this first part it says, determine whether each relation is a function, then state the domain and the range. So on this one right here, we've got this graph. So here's f. You'll notice this is a vertical line, and it definitely would not pass the vertical line test. So what we're going to write here is we're just going to write relation. We'll write relation, and then we'll do the domain down here. The domain for this, if we squish this onto the x-axis, the only thing that would be covered is a 3. So I'm going to do my best at making some set brackets right here. So that's just a 3. And then the range, if we were to push this over onto the y-axis, we'd have answers way down here going all the way up here. So the range is from -infinity to infinity, and of course round brackets around there. Okay, the next one, this is g. It does pass the vertical line test, so I'm going to say that this is a function. So we're going to go ahead and state what the domain and range are here. So the domain on this, if we were to squish this onto the x-axis, these points would come down here. These points would come up here. So we've seen this time or two before. This is from -infinity to infinity. And the range, if we squished all of these points over onto the y-axis, all of this would be covered. And then all the way down here. So we'd have a range from -infinity all the way up to +infinity. We can have every type of function value come out of this. So this is going to be from -infinity to infinity. And then we'll take a look at h over here. This is kind of a unique one. It's kind of this U shape going sideways. This does not pass the vertical line test, so this is not a function. This is just a relation. So we'll put relation right here. And then let's squish everything onto the x-axis. So these points would squish down here, these would squish up here, and there are no values over here. So the domain on this one is going to go from -infinity, we start way over here, and then we go all the way to this point right here, so all the way to 0. It's going to be around in the infinity, but let's take a look right here. It does actually hit that value right there, so we're going to make that a square bracket. And then let's talk about the range here. The range, remember, this continues to go out and down here and out and up here. So we would have some points over here that we could squish over on the y-axis, here. All of these would squish onto the y-axis. So we really get values way down here at -infinity all the way up to +infinity. Even though you can't see that it goes down that far, we do assume that on a particular graph like that, that's what it's going to look like. So the next part of this says, find the function value for each graph above or state why there's a problem. Well, we know on a relation we might have a problem, so let's take a look at this one here. It says find f of 3. It's really not even proper notation to have that f there because it's not a function, but if we look over here at 3, this means we go to 3 on the x-axis and then we figure out where the function is. So there's not a function value here for a couple of reasons. First, we put not a function. And second, we'll put too many y's to choose from. Too many y's to choose from. Okay, and that's the big problem with a relation as opposed to a function. Let's take a look at the next one. This one is a function, so we should be okay finding g of 3. Again, we're going to go to 3 on the x-axis, and then we're going to either go up to the function or down to the function. And this one we happen to go down, so that point right there, that point is 3, -6. Again, there's the x value, there's the function value. So the function value on this is -6. Again, we can kind of see that right there. And then on this one, it says h of 3. Well, if we go over to 3, that's not even in the domain, okay? So not a function, first of all, and 3 is not in the domain. 3 is not in the domain. Okay, let's slide down here and let's take a look at this next problem. It says determine whether each relation is a function, then state the domain and range. So we had graphs up above. This is a set of ordered pairs, and this is in a table. We can deal with that. Now remember, a function means that each x can correspond with only one y. So one way we can go through and check this is, are all of these x's different? If they're all different, then we know we've got a function. So we've got a 0 and a -1 and a 3. So this one is a function. So we'll put function right here. And then we'll write down the domain, and then we'll write down what the range is. Let me make that look like a D there. So the domain is going to be the set of 0 and -1 and 3. Okay, and then the range is going to be that 0, a 2. And remember, if we've already got a 2 in that set, we don't need to put another one. So I'm just going to stop right there. And then over here, let's see, do we have all different x's? We do, so this is going to be a function. So we'll go ahead and write function there. And then the domain is going to be the set of x's. These are the numbers that we'd put in, the independent variable, if you want to think of it that way. So 4 and 2 and 1 and -2. And again, I'm not really concerned that these are out of order numerically. They're in the order that they come on the function in the table. So we're going to go ahead and write down the range. The range would be 0 and 3 and -1 and 2. Close those brackets and we're in good shape there. Now, as we take a look at the bottom here, it says use these functions for the problems below. And we've got two different functions defined. So we've got f of x is 2 over x minus 1, and then g of x is 4x minus 5. And what it says first is, what is the domain for each of the functions above? Well, this is where you have to think back to the fact that there are only two operations that we know of so far that cause domain issues. One of them is dividing. We can't divide by 0. And the other one is taking an even root of a negative. So if we've got division in a function, we've got to be careful. If we've got an even root in a function, we've got to be careful. Well, this one doesn't have either one, so we're in good shape there. But this one has division. So what we want to check for there is what would make that equal to 0. So when would x minus 1 equal 0? If I just add 1 to both sides, that would be when x is equal to 1. So that's the only thing that we can't plug in here, because if we put a 1 in, that's 1 minus 1, and that would be a 0 in the denominator. So we're going to say this. You can put in anything you want, any real number from -infinity to infinity, as long as x is not equal to 1. And that's how we'll state that. And then the domain for this function g of x, there's no division in here, there's no even roots, so we can plug in anything we want. So the way we say that is we can just say that it goes from -infinity to infinity. Again, occasionally, I think we mentioned this before, some people will say that this is all real numbers. You can plug in any number that you want. That's another way of saying the same thing. All right, now we're going to do a little bit of evaluating functions. So we want to find f of 2. So this means wherever there's an x, we're going to put a 2. So this means we're going to have a 2 on the top, and then we're going to do 2 minus 1 right here. Now, because this is a positive number, I'm not as concerned about putting that in parentheses. So this is going to be 2 over, this is 2 minus 1. So the answer there is going to be 2. So f of 2 is actually 2. Let's take a look at this next one. Again, we're dealing with the function f. So wherever there used to be an x, we're going to put a -5. So we've got a 2 on the top, and we've got a -5 minus 1. There's a 2 on the top, and this is a -6, so we can reduce that. That ends up being -1/3. 2 goes in here once, 2 goes in here 3 times. So f of -5 is equal to -1/3. Again, I'll circle that, and remember what this means. This means the point 2, 2 is on that graph. This means the point -5, -1/3 is on that graph right there. So we've got 2 points that are on the same graph here. Now let's turn our attention to g of 1/4. Now we've got a fraction to plug in here. This may or may not be ugly. So let's go ahead and take a look at this. Wherever there's an x, we're going to put a 1/4. So this is 4. And then because it's multiplication and it's a fraction, I'm going to make sure I put that in parentheses. And then we're going to subtract 5 from there. If there's a fraction in the problem, you might as well think of everything as a fraction. So we're going to go ahead and cross-cancel the 4s. Those would cancel to be a 1. So this is going to be a 1 minus 5, so we get a -4 there. So I'm going to do g of 1/4 is equal to -4. So that means the point 1/4, -4 is on the graph. And then just continuing through on these guys right here. So this is going to be a 2. We're going to put a -3 where there used to be an x. So this is a 2. Whoops. That should have been a 1 there. Let's see, talking and writing at the same time didn't work. So we've got a 2 on the top, and we've got a -4 on the bottom. So we'll go ahead and reduce that. That's -1/2. So the function value at -3 is -1/2. Again, there's our point that would be on the graph. And then let's plug in a -4 here. So this is 4 times, wherever there used to be an x, we're going to put a -4. So 4 times -4 minus 5, that's -16 minus 5, so we end up with -21. So g of -4 is equal to -21. Make that look a tad better there. Circle that. And on to the last one on this page. So again, g of -10, we're going to plug in a -10 wherever there's an x. So this is 4, negative 10. We've got that minus 5 there. That's going to be negative 40 minus 5, so we get negative 45. So g of negative 10 is negative 45. So we'll go ahead and circle that, and we're all set to go. We're now on this second page, and we've got some different functions to deal with here. We've got h of x and we've got p of x. Notice that we've got a squared variable here plus another linear type term. And then we've got an exponent right here. So we've got 2 raised to that power. So whatever we plug in, we're going to put it in the exponent there. So we're going to need to be a little bit careful here. Again, the question here is what's the domain of each of the functions above? There's no square roots or fourth roots or anything weird like that, and there's no division. So the domain for both of these is going to be negative infinity to infinity. We're going to be able to plug in anything that we want into either one of these. We're not going to have to worry about that at all. And then we want to find h of negative 2. So here's h. Wherever there's an x, we're going to put a negative 2 in both those places. Now, because this is negative and we've got some squaring and some multiplication, I'm going to make sure I put parentheses around everything. We've got negative 2 squared. Remember, the exponent applies to everything that it's over, everything in the parentheses. So we've got 2 negatives and 2 2's, so this is going to be a 4. And then this is going to be 3 times negative 2. That's going to be a negative 6, so we get a negative 2. So oddly enough, h of negative 2 is negative 2. So I'm going to go ahead and circle that guy right there. And on to the next one, p of 2. So we're going to put a 2 wherever there's a x in that one. So this is going to be 2 to the second plus 4. 2 to the second, that's 2 raised to the second power. That's 2 2's. So that's going to be 4 plus 4, so we end up with 8. So p of 2 is equal to 8. And then h of 1/2, a fraction to deal with here. So let's see how this goes. Here's the function h. So wherever there's an x, we're going to put a 1/2. So this is going to be 1/2, and we're going to square that. And then plus 3 times 1/2. Now we know we've got fractions here, but let's try and deal with this without a calculator if we can. Remember, the exponent applies to both the top and bottom separately. So this is 1 squared over 2 squared. So that's going to be 1/4. And then this is going to be 3 times 1/2. I'm going to think of that as 3 over 1. So this is going to be 3 times 1 on the top and 1 times 2 on the bottom. Let's go ahead and get a common denominator here. 1/4 plus, let's see, in fourths, we double that. So we double this, so that's going to be 6. So that's going to be 7/4 here. So what that means is h of 1/2 is equal to 7/4. So it would go through the point 1/2 comma 7/4. So some fractions there, but we can deal with that. Let's take a look at p of negative 1. Again, we're dealing with this exponential right here. So this is going to be 2 to the negative 1 plus 4. Remember what a negative in the exponent means. It means reciprocal. So this is going to be 1 over 2 to the first, or that would be 1/2, plus 4. So this is going to be 4.5. And we normally don't write those as mixed numbers. We'll write them as improper fractions. So 2 times 4 is 8. Plus 1 is going to be 9. So this is going to be p of negative 1 is equal to 9/2. Go ahead and circle that one. And then we get a couple of interesting things going here. This one asks us to find p of q. So what we're going to do is wherever there used to be an x, we're going to replace it with a q. So this is going to be 2 to the q plus 4. Now the awesome part about this is there's no simplification that we can do here, so we just circle that. We're done right there. That's 2 to the q plus 4. And then on this one, we've got h of 4x. So wherever there used to be an x, we're going to put a 4x in both of these places. So let's go ahead and put a 4x here. And again, if I were to just put a square right there, it would look like 4x squared. It's not. It's 4x, and then we square both of those. Really good practice to put those in parentheses. And then plus 3 times 4x. So we've got, let's see, the 2, that exponent applies to both of these things that it's over. So this is going to be 2 4's. 4 times 4 would be 16. And 2 x's, so that's going to be x squared. And then we multiply these guys together, that's going to be 12x. So that means h of 4x, instead of getting a number, we actually get a variable expression like we did on this last one. So those are kind of interesting ones, a little funky, but they're really good things to practice. Let's slide down here and take a look at the next little bit. It says use the graphs below to answer the following questions. So we've got these pictures. We've got f of x, g of x, and h of x sitting right here. And it says identify the graphs below as piecewise linear or exponential. Well, remember, linear means it's a line, so that's this one right here. So this one's going to be linear. We also talked about this type of parent graph, this type of general shape that we're going to be working with a lot. This is an exponential, so we'll write exponential. Exponential. And that means this last one has to be piecewise, but you can kind of tell that. Remember, the name piecewise comes from the fact that it comes in several pieces. We've got a piece right here, then a piece right here, and then a piece right there. So this is going to be a piecewise function there. And then write the domain and the range for each of the graphs below using interval notation. Again, with a linear function like this, it's going to cover everything on the x-axis from negative infinity to infinity. And then because this continues going up, it's going to cover this part of the y-axis, and it continues going down, it's going to cover that part of the y-axis. So this is going to be from negative infinity to infinity for the range there on that linear function f. And then on G, this one runs along here and then it goes up like this. So the domain, we cover everything going this way, and then these points would be able to squish down here and cover everything there. So again, just like we had before, there's nothing weird about either one of these, no division, no even roots or anything strange like that. So we get negative infinity to infinity for the domain. And then when we squish this onto the y-axis, there are no points down here, but we start getting points right there, and then we go all the way to infinity. So we go from 0 to infinity. And then remember, this never actually comes down and touches the x-axis. That's like an asymptote. So it never actually touches there, so that's going to be 0 with a round bracket. And then this one's interesting. We've got closed points on the end of each one of these. This point would come down here at -4. This point would come down here at 3, and we've got everything in between. So let's make sure we go in the correct order. -4 to 3, square brackets on both of those. And then in the y direction, we don't get any answers down here until we get right here. We've kind of got some double coverage from either side up until 1, and then these points over here would kind of squish onto the y-axis, but then we don't get any above 3. So it's going to be from -1 all the way up to 3 in the y direction, and those are square brackets around there. Okay, let's slide down here and take a look at what we've got for 23, and then some of the other ones down below here. It says describe each below as increasing, decreasing, constant, or a constant on its domain. So this one right here, this is definitely going to be decreasing. It's going down from left to right. And then this one's going up from left to right, so this one's going to be increasing. And then this one, we've got a portion, an interval where it's going down, then it's flat, so that would mean it would be constant right there, and then it's increasing over here. So I'm going to just write that this is a combination on its domain. We've got a little bit of decreasing, a little bit of constant, and then a little bit of increasing. And then it says state the x and y intercepts for the graph above and write them as ordered pairs. So let's see, for the X intercept, that's going to be where it crosses the x-axis. So that's right here. And notice that we've got -4. That's the x coordinate. We're saying where it crosses the x-axis. And we don't go up or down, so that means the y coordinate is going to be 0. So there's our X intercept. And then the y-intercept is going to be this point right here. So we don't go right or left. So the x-coordinate is 0 this time. And then we go down to -2. So there's the y-intercept. And I'm going to follow suit with these guys right here. So let's try and find the x-intercept on this one. This is would be where it crosses the x-axis. But remember, this comes down here and gets really, really close, but never touches the x-axis. So there is none. And then for the y-intercept would be right there. So that would be 0, 1. And then let's take a look at this one. We want to find where this one crosses the x-axis. Well, this is kind of unique because it crosses in 2 different places. So one of them is -2, 0, and the other one is about, gosh, we'd say that's about 1.5. So I'll put that both of those are x-intercepts. And instead of writing a decimal, I'm going to go ahead and write that that's 3/2, 0. And again, we're not saying it's perfectly there, but it looks like it's somewhere in between there. And then the y-intercept would be right here, so that's going to be 0, -1. The last part of this asks us to find the average rate of change for the functions on those indicated intervals. So let's go ahead and take a look here. Remember, when we find the average rate of change, here's what we need to do. We always do the second x minus the first x. So I'm going to do 1 minus 0 here, and I'm going to do 2 minus 0 here. And then we need to find the function value at 1. So this is going to be f of 1 minus f of 0. And this is going to be f of 2 minus f of 0. So let's go ahead and calculate what we've got here. So this is going to be a 1 minus 0 on the bottom, and then I need f of 1. I need the function value at 1. So we're going to go down 1, 2, that's 3, so about 2.5, about minus 2 1/2. Now, we normally don't write things as mixed numbers, so let's go ahead and change this. Let's change this so this is negative 5/2, negative 2.5, and then minus whatever the function value is at 0. So we go to 0 on the x-axis, and then we're going to go down here to negative 2. And notice when we've got a minus minus, that's going to turn that to a plus. So we've got negative 2.5, which is right up here, plus 2. So this is going to end up being negative 1/2, and then we've got a 1 on the bottom. So negative 1/2 divided by 1 is just negative 1/2. So I'm going to go ahead and circle that. And we've encroached on the other one, so let me draw a line so we don't run into that one. And then on f of 2 minus f of 0, so we're going to have 2 minus 0 on the bottom, so that's just going to be a plain old 2. And then f of 2, this is down 1, 2, 3, so this is going to be negative 3 minus whatever f of 0 is. So this is going to be minus 1 and 2. So there's that minus minus 2 again. We're going to put a plus here. So this ends up being negative 1 on the top and a 2 on the bottom. And lo and behold, we get exactly the same shape here, okay, and the same slope. So let's take a look at g. So on this one, again, we're going to do the same thing. So I'm going to go ahead and write 1 minus 0 here because we're finding it over that interval. And I need g of 1 minus g of 0. Now, I'm hoping these work out a little bit better than the last one. So we have 1 minus 0, that's going to be a 1. And then g of 1, so that means the function value at 1, so that's going to be a 2, minus, let's find the function value at 0, so that's going to be a 1. So this is 1 over 1, so the answer there is 1. Now, this is the same as the slope of the secant, so if I were to draw a line between the two of those, that sure looks like it has a slope of 2, or sorry, slope of 1. And then let's do this guy right here. This would be g of 2 minus g of 0 over 2 minus 0. Now, we can continue doing this, or I've done several of these using the average rate of change formula. We have a graph on these, so I'm going to run through here and show you, just like we did here, that we end up with the same answer if we use the rise and run idea. So I'm going to go from here to here. We rise 1 and we run 1. So that would be 1 over 1. We get a slope of 1. Now, if I were to erase that and come back here and say, hey, I don't want to find the slope between 0 and 1. I want to find the slope between 0 and 2. So 2 would be right here. So we want to draw a line, a secant line from here to here. So we're going to go up this far. We're going to go up 3, and we're going to go over 2. That's a rise of 3 and a run of 2. So we'd have 3 over 2. So we end up with that for the average rate of change. Okay, slope of secant and average rate of change are the same thing. And then on this next one, I'm going to do this just using the graph. So here's what we're going to do on this one. We want to find the average rate of change between 0 and 1. So that's going to be between 0 and 1. So between this point and this point. Well, if you take a look at that, that's perfectly flat. So the rise is going to be 0. The run's going to be 1. So we get an average rate of change, or a slope of a secant, of 0. And then we want to go between 0 and 2. So x equals 0, that would put our point down here. X equals 2, that would put our point right here. And then the secant line would look like this. So let's find the average rate of change there. So we're going to go up 2, up 2 and then right 2. So there's our little slope triangle, up 2 and over 2. We get 2 over 2, so we get a slope of 1. Okay, so I did several of these using the average rate of change formula, and because we had a graph, it makes it pretty easy just to use that rise over run idea and the idea that we can just draw a secant and that the slope of the secant is the same as the average rate of change. Now, one last thing I want to look at here is it says which function has the same rate of change for both intervals. Well, this one right here does, so that's going to be f of x does. Okay. And what's the reason for that? Well, it's a line. A line is going to have the same rate of change, the same slope everywhere. Okay, so we'll put it's linear, and lines have same slope. I'll put i.e. rate everywhere. Everywhere. Okay, so good thing to think about. We certainly didn't see that in the exponential one. That one has a different slope over here than it does right here and right there. Same thing with that piecewise function. We got different rates on different intervals. So good thing to keep in mind. All right, let's take a look at this last page. It says the following shows a savings account balance as monthly deposits are made. So as the months go by, you'll notice what's happening here. So deposits, they're putting money in, and you can kind of tell how much money they're putting in. It says, graph the data from the table, be sure to label and scale the axes. So I'm going to underline label and scale. Let's make sure that we do both of those. The labeling is pretty easy because this is like the X and this is like the Y. So I'm going to put months over here, and then I'm going to put balance up here. So balance, and I'll just put a $sign right there. That's pretty easy. Now the scaling is another story because we've got some fairly small numbers on the x-axis and we've got some fairly large numbers on the y-axis. And this is going to start at 6,000 and then it's just got to go up from there. So we've got to make sure that we have room for everything. So if we count the number of squares here, we're certainly not going to be able to go by ones, but let's say we go by 500. So this would be 500, then 1,000. 2,000, 3,000, 4,000, 5,000. We could fit 6,000, but then it just goes up from there and we wouldn't be able to fit very much. So 500 for each one of these marks isn't going to work. So let's maybe try 1,000. So this would be 1,000 and then 2,000 and then 3,000. This would be 4,000 and then 5,000, 6,000, 7,000, 8,000. And then this would be 10,000 up here. Okay, so that's going to work out right there. And then in months, I think we can go ahead and just count these in ones. So this would be 0, then 1, 2, 3, 4, 5, 6, and so forth. All right, let's go ahead and mark this down. So 0, 6,000. So that's going to be right here. And then after 1 month, we've got 6,400. So that's going to be about, let's see, that's 7,000. So it's a little less than halfway up. So we look about right there. Then 6,800, just shy of 7,000. One other thing that we could do with this was we could have drawn like a broken axis and then stretched this out a little bit, but we're on our way now. So let's just go ahead. So on month 3, it's 7,200. So about right there. And then on 4 months, it's 7,600. So 7,600 would be about right there. Well, you'll notice that we're adding the same amount every single time. So this is going to kind of just continue going up by the same amount. So another 400 would put us at 8,000, then 8,400, then 8,800, then 9,200, and so forth. So it just continues to look like that. So this is linear. And the reason it's linear is it makes a straight line, and we could also say this has the same rate or the same slope all the way through, which brings us to the next question. It says, what is the slope? Well, we can tell from here to here it went up $400 in 1 month. So let's go ahead and write that down. It goes up $400 in 1 month. Okay, and by labeling that, we've kind of explained what that means, and I'll just go ahead and write one more time, $400 per month. Okay, and let's go ahead and write that it goes up there. And it says, what is the y-intercept? The y-intercept would be 0, 6,000, and of course that would mean $6,000. And then write a linear function for this situation. So again, we're thinking about linear functions, y equals mx plus b. In this case, I might write something like this. Again, you would be totally free to choose something else. I'm going to write 400t and then plus 6,000. And we're going to say t equals time in months, and b equals balance. Balance. Okay, in dollars. Okay. All right, let's slide down here and let's take a look at what else we've got. What does the y-intercept represent? So the y-intercept represents the starting, so let me write that the right way, starting balance in the account. That sometimes is called the initial balance or the initial amount. Okay, what would the x-intercept represent? Okay, that's kind of an interesting question here. What would the x-intercept represent? So it doesn't hit the x-axis on this part of it, but if we were to kind of go back in time, it would come over here and it would hit the x-axis somewhere back here. And if we're counting in months, let's see, what would that represent? So that would be something comma 0, some x value comma 0, or the way we're marking these, this would be some t value comma 0. So let's write this, the time when the balance was $0. Because remember, this is the time in months, and this is the amount of money in the account. That's what the X-intercept would represent. Haven't talked very much about that, but that's kind of an interesting question. What is the independent variable? Remember, the independent variable is always going to be the horizontal one. It's going to be the x-axis or the equivalent. So we're going to put time. In other words, that's the months. Okay, whoops. Months. That's an abbreviation for months. And then what's the dependent variable? Dependent variable, of course, is going to be the amount in the account or the balance. Okay, so we're going to put the balance is the dependent variable. The balance in dollars depends on how much time has gone by. And then we've got an interesting question here. Is this going to be discrete or continuous? So let's go back up here and notice what happens. It says in the setup of the problem, it says this table shows the savings account balance as monthly deposits are made. So it doesn't cover all of these values in between. It jumps from this dollar amount to this dollar amount to this dollar amount and so forth. So you can see it jumped from $6,800 to $7,200. So we're going to say that this is discrete, but I do want to point out one more thing, okay, before I explain this. And that is another way that we could graph this, and we won't get into this in this class, but just keep this in mind for the future. The balance actually stays $6,000 for that whole month, and then it jumps up here, and it stays at $6,400 for that next whole month. That's actually called a step function. It's another type of function. It's a discrete function. So just keep that in mind, but for the time being, we're just going to leave it like that. And the reason that it's discrete is it doesn't cover all the dollar values. So we'll say doesn't cover all dollar values. Doesn't cover all the dollar values, and it kind of skips from month to month to month. It skips from, the balance in month 1 to the balance in month 2 and so forth. And then clearly this is increasing, and the reason for that is we are depositing money. And another reason for that would be this: we have a positive slope. We have a positive rate. That's really the reason there. Okay, and then it says use the function that you wrote to find f of -1. So we're going to find b of -1. So b of -1 is equal to 400. I'm using this function right here, times -1. We're replacing wherever there's a t or an x, we're going to put a -1, and then plus 6,000. So what we end up with is -400 plus 6,000. So we get b of -1 is equal to, let's see, -400 plus 6,000. That's going to be 5,600. So we'll go ahead and circle that. And it says, what would this represent? Well, let's see. -1 would be going this way. So instead of going forward in time every single month and depositing money, what we're doing is we're figuring out how much money there was a month ago in the account. All right, so let's go ahead and write that down. Balance 1 month ago. 1 month ago. Kind of going back in time in that one. And then it says, let's see, use the function to determine the balance of the account in 10 months. So that's going to be the balance in 10 months' time. So we're going to do 400 times 10, and then we're going to add the 6,000. So let's see, 400 times 10, that's 4,000 plus 6,000. So the answer on that one is 10,000. And let's go ahead and put a dollar sign on there because there's going to be $10,000 there. And then it says on this last part here, it says if you found the average rate of change between months 0 and 2, would it be different than the average rate of change between months 2 and 4, and explain your answer. So we're going to come back here and we're going to take a look at this. So if we were to find the average rate of change between 0 and 2, months 0 and 2, it went up $800 in 2 months, so that's $400 per month. And months 2 and 4, it went from $6,800 to $7,600. So again, that's $800 in 2 months. So again, that's $400. So would it be different? The answer to that is no. And one really good reason is it has the same rate, and it has the same rate because this is a linear function. No, comma, this is a linear function, so it always has the same rate. So we'll say, so it always has same rate. And we're also going to put slope right next to that. Okay? All right. A lot of work on this practice test. Lots going on there, but really good stuff. Good things to keep in mind. Test is going to be shorter. Good luck on the test.